Welcome back to our chemistry series. Today we're going to be diving into the concept of resonance. This will be a very introductory video, and there'll be some more following this that kind of go into more detail. But today we're just going to introduce the concept of resonance. So resonance refers to the idea that multiple Lewis structures can be drawn for a single molecule. These structures are not different molecules, but different ways of representing the same molecule. So let's take a look at acetate. In acetate, we can draw multiple Lewis structures by moving pi bonds, formal charges, and lone pairs of electrons. These are all things we're allowed to move. However, it's important to remember that we should never alter the sigma bonds, which is your single bonds. Double bonds will be the pi bonds. And this is because if we move the sigma bonds, it completely shifts the framework of the molecule altogether, which completely changes the properties of said molecule. So when we do resonance, we have to keep in mind that we can only shift the pi bonds, the formal charges, and the lone pairs of electrons. The goal is to rearrange the electrons, not to change the molecule's entire structure. A crucial point to note is that you'll never find an isolated molecule that looks exactly like one of its resonance structures. Instead, the true molecule is a resonance hybrid, which means it's an average of all of the possible resonance structures. The hybrid concept will be covered in more details in a separate video because there's quite a bit to unpack there. Now let's go over the resonance structures of acetate. In your homeworks, you'll often be asked to show arrows of where the electrons are going and where the bonds are shifting, so we're going to do it that way. Let's take a look at this acetate right here. Something that we notice is that there's a double bond right here, and there's a formal negative charge here. So these are two things that we can move. So let's go like this. We'll do an arrow of the double bond going to this spot, and we'll do the lone pair of electrons that causes negative charge to happen and move it on top of this bond here. Now that we have an idea of where we're going, let's redraw this molecule. So we'll do an arrow like this to denote that there is a resonance structure present, and then we'll start to redraw. We have our carbon in the center. We have this CH3 over here, unchanged. And now we have a double bond going down to here because we moved that lone pair of electron down to the single bond. And now we have two lone pairs remaining, meaning we have a neutral oxygen. On the other hand, up here, since we moved that pi bond towards the oxygen, what we're going to have here is a single bond and three pairs of electrons around this oxygen and a negative charge. So this is a resonance structure of acetate. And as you notice, no sigma bonds were shifted. This is the same molecule, but it's just rearranged a little bit in ways that keep it the same. Something worth noting is that with ions like this that have a negative charge is that the charge of the resonance structure must be the same to the original charge. So if it comes in as a negative, it has to come out as a negative. Another interesting thing about resonance is that they often have multiple structures. So in the case of acetate, there's actually another structure that we can draw. If you look closely here, and something worth noting is that this will not be a favorable structure. We'll go over the concept of major and minor contributors to resonance in a future video. But that being said, it's still a resonance structure possible. We'll draw another arrow to denote that we have a resonance structure at hand, and let's take a look at the molecule that we just made. Something that we can do is move this pi bond onto the oxygen here. We'll go like this. Now let's redraw our molecule. Once again, we have the carbon in the center, we have the CH3 off to the side, and we have our oxygen with a negative charge up here unchanged. However, what we have now is a sigma bond coming to this oxygen, and we have three pairs of electrons and a negative charge. So how could this be possible? Because we have two negative charges on our oxygens and only one on the previous structure. Well, the carbon in the center now has a positive charge because carbon, as you remember from the Honk principle, likes to have four attached bonds to it, and it's missing one. So in this case, it has a positive formal charge. And what we get is the negative and the positive cancel each other out, and we have one negative charge remaining. So while not overly favorable, this is in fact a structure of acetate that is a possible resonance structure. That's going to be all of the new information I present, but if you want to stay a little bit longer, I do have one more example problem. Let's look at NO2 minus, or a nitrite ion. We'll draw it out like this. So we have our oxygen here. We'll put 2 lone pairs on it. We'll go double bond. As you remember from the Hong principle, nitrogen likes 3 bonds to it. Put this down here, a single bond off of it. We'll satisfy our octet rule, and we'll add oxygen with 3 lone pairs and a negative formal charge. With this, as you may notice, there is a double bond and there's a formal charge, and these are both things that we can move. So let's go like this. We'll bring this double bond over here, this pi bond, put it on the oxygen, and we'll take one of the electrons over here on this oxygen and take it towards that sigma bond. And now we'll draw our NO2 minus resonance structure like this. We'll have our nitrogen in the middle, unchanged. Now we have a double bond over here, an oxygen, and only 2 lone pairs of electrons, making it neutral. And we have a single bond over here with an oxygen that has 3 lone pairs of electrons and a negative formal charge. And as you can see, this is unchanged, and it has the same formal charge as it started off with. Understanding resonance is essential for grasping the true nature of molecules in chemistry. Remember that the resonance hybrid is the real representation of the molecule, which blends all possible structures into one. We'll go over that in a future video, but stay tuned for our next video where we'll dive deeper into resonance contributors and decide which resonance structure is the one that is preferred. Thanks for watching, and don't forget to like, comment, and subscribe for more chemistry insight.